Hi, I'm Yangyang Feng from Tsinghua University. I will introduce our work, Mobius, Fine-Tuning Large-Scale Models on Commodity GPU Servers. Since the birth of Transformer, the machine learning model size has increased by 28,000 times. Training models with such large scale requires enormous computing power. For example, training GPT-3 requires 3,640 petaflop per second day. From the perspective of time, it costs 30 years to finish training if we just use an A100 GPU. From the perspective of money expenses, training GPT-3 needs around $4.5 million. Fortunately, many large companies previously trained these large models on large datasets, which are called pre-trained models. These pre-trained models can be fine-tuned on small datasets for specific downstream tasks. Compared with pre-training, fine-tuning requires much less computing power. It's a great idea to fine-tune large-scale models on commodity GPU servers. The price of commodity GPU servers is much lower than that of data center GPU servers. For example, a data center GPU server with 4 fully connected A100 GPUs costs up to $100,000. Buying a commodity GPU server with 4 1390 Ti GPUs only needs $10,000. Although commodity GPU servers are cheaper, they provide sufficient computational power. However, communication resources are scarce in commodity GPU servers. First, the bandwidth of inter-GPU communication in commodity GPU servers is low. In data center GPU servers, GPUs are fully connected via NVLink, which enables up to a 900 GB per second bandwidth between any two GPUs. However, commodity GPU servers do not support fully connected NVLink. Thus, their inter-GPU communication only reaches a bandwidth of PCIe bus around 10 GB per second. Second, there are serious communication contention problems. GPU direct peer-to-peer enables GPU-to-GPU data operations directly over the memory fabric. However, it is unavailable on commodity GPU servers. Therefore, inter-GPU communication is first routed through CPU to DRAM and then transferred to the target GPU. If two GPUs share the same CPU root complex and communicate at the same time, there will be communication contention and the CPU root complex. Unfortunately, existing large model training systems communication pattern mismatches with commodity GPU servers' scarce communication resources. We collect communication traffic when fine-tuning some models use deep speed on a commodity GPU server with 4 GPUs. Deep speed generates communication of 7.3 times the model size in one training step. For communication contention, when training the 15 billion model, most data communication of deep speed only reaches 15% of the maximum bandwidth of the GPU root complex. The shutdown shows that communication bottlenecks the 70% of training time. In this paper, we propose Mobius, a communication-friendly training framework. Mobius uses heterogeneous memory-based pipeline training to train models on multiple GPUs using DRAM and GPU memory. To enhance the efficiency of the Mobius pipeline, we introduce Mobius Partition to find the optimal model partition scheme, and then we propose cross-mapping technique to map the model partitions to different GPUs, reducing the communication contention. In Mobius pipeline, a model is first partitioned into some stages, each of which includes multiple layers of the model. These stages are first stored in DRAM. Unlike the traditional pipeline parallelism, the number of stages can be more than that of GPU, and each GPU is responsible for multiple stages execution. Before training, each GPU fetches the first corresponding stage to the GPU memory. We use Fig to denote the ith stage's execution on the jth microbatch. During training, the first microbatch is computed on stage 1 on the first GPU, and then the result is transferred to stage 2 on the second GPU. At the same time, the second microbatch is computed on stage 1 on the first GPU. Other microbatches computing are similar. During executing the stages on the GPU memory, each GPU prefetches the next stages that are going to be executed. However, due to CPU root complex sharing, there may be communication contention indicated by the red squares in the slide. After finishing executing some stages, the corresponding GPU memory is freed and the GPU continues to execute the next group of stages. There are two questions to answer when partitioning the model. First, how many stages are in each GPU? The second question is how many layers are in each stage. To answer the question, Mobius first profiles some metrics. It profiles each layer's memory footprint and computation overhead. Then, it also profiles hardware performance, including inter-GPU bandwidth and GPU to DRAM bandwidth. Finally, Mobius leverages mixed integer program according to these profiled metrics to find the optimal partition scheme. In the MIP, the objective is to minimize the training time of a step. There are two groups of constraints. The first one is about memory. The computing data and prefetching data stored in GPU memory should not exceed the GPU memory. The second one is about pipeline order. Stage and microbatch execution order should not influence the convergence of model training. More detailed descriptions about MIP are in the paper. Communication contention results in a computation bubble influencing training efficiency. Look into the cause of communication contention. The prefetching time of adjacent stage is so close that GPUs need to communicate at the same time. The possibility of communication contention is much higher if two adjacent stages are mapped to the GPUs under the same CPU root complex. On the contrary, the prefetching time difference of two non-adjacent stages is larger, which provides us the opportunity to solve the communication contention problem. Therefore, we need map adjacent stages to GPUs not under the same CPU root complex. To model the idea, Mobius uses the equation to estimate the contention degree between two stages. Shared Ig is the number of GPUs under the same CPU root complex, where stage I and stage G are located. Absolute value of I minus G indicates the time difference to upload the two stages data. The more GPUs are under the same root complex, or the smaller difference between I and G, the more likely is to conflict. Mobius searches all mapping schemes and finds one with minimal contention degree. We evaluate one-step training time on models with different scales. We compare the performance of Mobius with that of G-Pipe, deep speed with pipeline mode, deep speed with heterogeneous memory mode. G-Pipe and deep speed with pipeline mode only leverage GPU memory. Therefore, it runs out of memory when training models with larger scale. Mobius and deep speed with heterogeneous memory mode leverage DRAM and GPU memory, enabling training larger models. Mobius decreases per step training time by 4.1 times on Turbo 2+2 server, and 4.8 times on Turbo 1+3 server. This is because deep speed with heterogeneous memory mode suffers more from communication problems on commodity GPU servers, while Mobius alleviates with Mobius Partition and cross-mapping technique. In Turbo 1+3, Mobius brings more significant performance improvement because there are more GPUs sharing the same CPU root complex, causing more severe communication contention. To verify that Mobius solves the communication problems on commodity GPU servers mentioned before, we collect communication traffic and bandwidth statistics. For communication traffic, Deep speed with heterogeneous memory mode needs to transfer 7.3 times the data of a model, while Mobius only transfer about 1.8 times the data of a model. This is because deep speed with heterogeneous memory mode needs frequent collective communication to synchronize the training results between GPUs, while Mobius only needs to transfer a small amount of activations between GPUs. For communication contention, we collect the bandwidth statistics. The maximum bandwidth measured is 13.1 GB per second. The CDF shows that in Mobius, most data is transferred at a bandwidth of more than 12 GB per second. However, deep speed with heterogeneous memory mode transfers most data at bandwidth of less than 6 GB per second. This verifies that Mobius effectively mitigates communication contention problem. Finally, there are some briefly conclusions. Commodity GPU servers is a more affordable option for fine-tuning large-scale models. It is cheaper than data center GPU servers and provides sufficient computing power. However, the communication resources on commodity GPU servers are scarce. Therefore, we propose Mobius, a communication-friendly large-scale model training framework to cater for scarce communication resources on commodity GPU servers. In Mobius, we use heterogeneous memory-based pipeline training scheme to enable larger model training. To enhance Mobius Pipeline, we propose Mobius Partition to find the optimal partition scheme and the cross-mapping to mitigate communication contention. From the evaluation, Mobius significantly reduces the training time by 3.8 times to 5.1 times compared with prior art. Thanks very much.